Welcome, class. We are going to cover chapters 7, 8, and a little bit of 17. So chapters 7 and 8 talk about atmospheric forces and pressure. And then in 17, in general, the chapter talks about mountain windstorms, but we're going to look more into Santa Ana winds, which is what you're seeing in the background. This is a wildfire that basically was expanded and grew more intense because of Santa Ana winds. So these are some questions that we're going to investigate. I want to talk about sea level pressure, the causes of wind, both for speed and direction, what geostrophic and gradient winds are, what happens in the upper levels of our atmosphere, and what causes Santa Ana winds. So just like in my other lecture sets, there are various terms that we will get into as we get farther into the chapter. So some of the terms that you may have heard of before, like friction. Friction is an interesting force that we have at the surface. You probably have heard of a jet stream, so we're going to talk about jet streams and jet streaks, and eventually we will get into Santa Ana winds. Like any chapter in a science course, there are a lot of different vocabulary, so it's very important for you guys to take notes while I lecture so that you can more easily remember and define some of these vocabulary and other concepts that I talk about. So in order to start, I just want to ask you, have your ears ever popped or had a strange sensation when you are either ascending or descending in an airplane or even going up and down over a hill? Well, the experience that you have has to do with atmospheric pressure. And as you know already, pressure decreases as we go up into the atmosphere. So that's part of the reason why your ears are affected. Now remember, the atmosphere is a fluid, just like water. There are some differences between air and water, but the physics behind air and water are very similar. So gases are in constant motion, moving all over in every direction. Now the force that's exerted by these gases is atmospheric pressure. That's how we define it. And this force is exerted on every surface that touches the gas. I usually like to constrain the definition of pressure into the weight of the air on top of you. So you can imagine that when we're near sea level, there's a lot of atmospheric gases or air above us, so we would have a greater force. And then that force decreases as you go higher up into the atmosphere. So this is another way of looking at the atmosphere. We're looking at molecules, and as you notice, there are a lot more molecules near the surface of the Earth than in the upper parts of our atmosphere. So pressure technically is force divided by area. And if we use an everyday unit, it's almost 15 pounds. So remember, the atmosphere weighs almost 15 pounds for every square inch of your body. That's actually quite a bit of weight. There is some buoyancy forces going on with the atmosphere that helps us not necessarily feel the entire 15 pounds per square inch, but nonetheless, that is your average pressure at the surface, or at sea level, I should say. We don't use pounds per square inch in meteorology, but we use millibars. A millibar is a unit of pressure, and the average unit of pressure is 1013. Technically, it's 1013.25. So if we take a look at various pressure readings that we've had across the surface, now remember, 1013.25 millibars, or if you want to use inches of mercury, it's 29.92. That's just average. A strong high pressure system can be up to 1040, and a deep low pressure system can be as low as 980. Now this is your typical range of pressures that you might see even here in California. Your typical range doesn't mean that pressure can not be outside of this range. It's just that's what's normal. And for our weather in California, actually that range is probably a bit smaller. We're going to get into this later, but I just want to point out now that strong high pressure systems tend to lead to clear sunny days, and around here, Santa Ana winds if it's in the right time of year. Deep low pressure systems are often related to your winter rainstorms. Now, the highest pressure ever recorded was 1084 in Siberia in December. Extremely cold weather can be very dense and can cause extreme amount of pressure. Now, cold air isn't the only way we can get a high pressure. We can also have air sinking. That creates a high pressure as well. And I mention that now because I don't want students to automatically think, ooh, cold weather means high pressure. Hot weather means low pressure. That's not always the case. And then an extreme low pressure at the surface was actually in a typhoon tip back in October 1979. 870 millibars at the surface is extremely low. One of the reasons why hurricanes and typhoons, which are generally the same thing, are so strong. So in order to understand pressure patterns, we have to draw lines of constant pressure. And isobars are those lines of constant pressure. As you see here, we have values there, we have 1020 over here on the left, we have 996 in the middle here, then back to 1024 on the right. So this plots our pressure across North America. And we'll learn later on why the wind behaves the way it does, and it has to do with differences in pressure. In a previous lecture, we talked a little bit about wind barbs, so we'll talk more about that in this set of lectures. So what are the forces that influence wind? Why do you think wind occurs? One time I was talking to a psychology major, and this person just had this belief that there was no way to understand why wind forms. Well, that's not necessarily true. There are forces that drive wind. The primary force behind wind, the ultimate force, is called the pressure gradient force. And it's simply just difference. If we have a difference in pressure over a distance, then we have a pressure gradient force. For example, look at this figure right here. On the left, we have a lot of air molecules. And so we can say that we have high pressure. On the right, we don't have as many air molecules, so we can say we have a low pressure. Remember, nature wants to find a balance. So in order to restore balance, these air molecules on the left will move over to the air, or to the part on the right. So air always goes, well, I shouldn't say always, air wants to go from high to low. And when we just have this force, it's actually directed perpendicular to those isobars. And it again goes from high to low. If we have a large change of pressure over a short distance, we can have very strong winds and a strong pressure gradient. This is the ultimate force that causes wind. We do have other forces that we're going to talk about, but this must be here in order to have wind. If we do not have a change in pressure over a distance, we will not have wind. You could think of air behaving like water, like I said before. If we have two tanks, one has more water, so let's say it's higher pressure, and then the other tank has less water, lower pressure. When you get rid of this X is supposed to represent, let's say, a block in this tube that's trying to get the water to go from high to low. If you get rid of that, then the water will move from the high to the low until the pressure between these two are the same, or in this case, until the water levels are the same. That's the basic idea behind pressure gradient force. Okay, another force that we deal with, and it's a little bit tricky to understand, it's the Coriolis force. The Coriolis force is due to the rotation of the Earth. Any free-flowing object, such as wind or even ocean currents, airplanes, rockets, they all get affected by this Coriolis effect. Sometimes we say effect because it's technically not a true force. It's an apparent deflection. But in this case, we'll probably use Coriolis force and Coriolis effect interchangeably. Now, the effect is very simple to remember. Coriolis force moves the wind or whatever object to the right in the northern hemisphere and to the left in the southern hemisphere. So air that tries to go from high to low may actually get deflected and never really reach the low. The stronger the wind, the greater the deflection. We do not see Coriolis at the equator, but we see the greatest effect at the poles. It only influences the direction, and it only impacts long distances. And I usually like to say a rule of thumb is anything that's bigger than 500 to 1,000 kilometers will have a significant impact by the Coriolis effect. So sometimes people think that the way their sinks and toilets and bathtubs drain, and if you ever look at this, it's rotating, and they believe that's due to the Coriolis effect. But remember, Coriolis only impacts things that have a long distance. So sinks, toilets, even tornadoes are not impacted directly by Coriolis. I encourage you to watch the 1 or 2 videos I have on Coriolis that's posted on Canvas so that you will better understand the Coriolis effect. So let's say for a minute here that we're going to represent the Earth using a merry-go-round. And this direction rotation is counterclockwise, which is true if we are looking down at the North Pole. So I'm going to put an NP here to represent the North Pole. Now, if this is moving, what's going to happen when this person throws the ball to the person across? It will actually be deflected if you are a person that's on the merry-go-round. So you have this apparent deflection, and if you see, it's to the right. If it were rotating clockwise, which represents the southern hemisphere, it would be deflected to the left. So sometimes I like to think about another more realistic example, and that is a flight. An aircraft flight, if we're just dealing with an Earth without rotation, very easily can go from point A to point B. Find the destination. But we live on a rotating Earth, and it doesn't matter what direction you're going. In the northern hemisphere, you will be deflected to the right. So if you start, let's say in Alaska, and you want let's say you want somewhere in eastern Canada to be your destination, if you do not account for Coriolis, you'll actually end up somewhere in, let's say, North Carolina. So pilots have to, well, they probably use autopilot, but in some way they have to account for the rotational direction of the Earth. Otherwise, they will not get to their destination. The only exception is if you're flying solely along the equator. If you're flying along the equator, we do not have any Coriolis. Only when we are away from the equator do we have Coriolis. Later on, when we talk about typhoons and hurricanes, the Coriolis effect is key for the rotational directions of hurricanes. And you will also note that hurricanes never exist at the equator because we do not have Coriolis there. So we have certain kinds of wind that can be a result of just pressure gradient and Coriolis force. And those are called geostrophic winds. Geostrophic. That basically means in the upper atmosphere, technically I should say the upper troposphere, the winds travel parallel to the isobars. And just like before, and kind of like a hose, if you squeeze a bunch of isobars together, the wind will go faster. Just like if you squeeze a hose, water will go out faster. So if you take a look at this diagram, we're starting somewhere off the coast of California, and this wind wants to go toward lower pressure. We have higher pressure here, and we have lower pressure here. It starts to go from high to low, but then because it's moving more than 1,000 kilometers or so, it starts to get deflected to the right. Now, the moment the wind has the pressure gradient force pulling it to the left and Coriolis pulling it to the right, and these forces are equal in strength, then we have a wind that is actually parallel to isobars. We call that a geostrophic wind. Here's another example. As you can see, the wind always starts by trying to go toward lower pressure. But if we're dealing with just pressure gradient and Coriolis, which is what we deal with in the upper troposphere, then you will get wind parallel to these isobars. And those are called geostrophic wind. What's nice about geostrophic wind is that we can simply plot isobars, or sometimes we call them contour lines, in the upper atmosphere, and we can get a good sense on the direction of the wind, because we know that that direction of the wind must be parallel to those isobars. If we have, another thing we can look at, if we have a tight spacing of those isobars, then the wind speed will probably be much faster than if we have, look at the wind speed over here. We don't really have a lot of isobars, so the wind speed is pretty slow. Again, this is just another example. We can use isobars or contour patterns in the upper atmosphere to get the general wind pattern, as long as we know where the highs and the lows are. Okay, so here's another diagram. This over here, once again, describes geostrophic wind. But one thing that I wanted to point out is what happens when we have rotation around a center of a high and low. So this is moving counterclockwise over here. It's rotating counterclockwise, whereas the high is rotating clockwise. So this is the result of the forces between pressure gradient and Coriolis and the rotational. We could include centripetal force in here, but we're not going to. In the southern hemisphere, everything is reversed. There would be clockwise rotation around the low, and around the high you would actually have counterclockwise. One of the reasons why we have that, as you can see here, we're looking at northern hemispheric cyclonic flow, which is just rotational flow around a high and a low. You can see as wind enters the low pressure system, it tries to go toward the low, but then the Coriolis force makes it go to the right. So then we have a constant rotation of counterclockwise. Vice versa here for the high pressure. This is just a zoomed in version if you want to take a look at those force arrows between pressure gradient and Coriolis. Same thing for the high. Now, if we're looking at clouds on a satellite image, we can pretty easily tell where our low pressure systems are. Remember before I mentioned that low pressure systems usually lead to storms or some kind of weather pattern that have clouds and rain. And eventually we'll learn that these systems can actually produce severe weather. So as long as we know what hemisphere we're in, we can deduce that the wind pattern will be counterclockwise around a low. And again, this has to be, we have to know which hemisphere we're in. So another term for curved isobars like this is a gradient wind. So gradient winds occur when we have just pressure gradient and Coriolis, and they're rotating, in a circular fashion around a high or a low. This is a low pressure system in the southern hemisphere. This is south of Australia. Notice that the rotation is clockwise because we're in the southern hemisphere. And again, this is called a gradient wind. Okay, so let's put these pieces together. We're taking a look at upper level patterns of wind and pressure. And so notice here, let me talk a little bit about this. We're not looking at isobars in the upper level of our atmosphere. What we do in the upper levels of our atmosphere is, instead of plotting pressure for a constant height, we plot height in meters for a constant pressure. We'll talk about that later in this lecture. So what you're looking at is the height of 500 millibar value, and this height that I just circled is 5,760 meters. So, but we can still use the same principle where if we have straight isobars or contour lines, we'll get winds that are parallel. By the way, this wind right here, this wind barb means that the wind is coming from the west. So the wind is actually coming from the west and moving east. So the gradient wind would be the examples where we have circular contour lines and winds going around it. So we have two examples here, at least two examples of gradient wind. But then this area right here where I labeled geostrophic wind, those lines are pretty much straight. We have straight isobars / contour lines. So again, we can use the spacing of these lines and whether or not they're straight or curved to get a good idea of how the wind is behaving in the upper atmosphere. Okay, so we talked about pressure gradient force and Coriolis. There's one more force we have to deal with. Again, there are other forces, but we're going to just talk about the three main ones. When we talk about wind at the surface, we have to add friction. So as a reminder, winds on upper level atmosphere, I should say troposphere, are typically parallel, and in around North America or in any mid-latitude, they flow from west to east. However, when we're dealing with surface winds, now we have to deal with the force of friction. Friction slows the wind down. As you can imagine, as wind is trying to flow across the surface, it encounters hills, trees, buildings, cars, and it slows the wind down. Now, if we slow that wind down, that decreases the effect of Coriolis. So instead of the wind flowing parallel to isobars, the wind flows at an angle, about 45 degrees. 45 degrees is pretty much the maximum angle that the wind will flow compared to the isobars. We could get as low as 30 if we have smoother terrain. Still wants to go from high to low, and it's not perpendicular like we had with just pressure gradient force. It's not parallel when we just had pressure gradient force and Coriolis. If we have all three, then the winds are crossing the isobars from high to low, but at a 45-degree angle, roughly. So this is just another graphic showing that we have a lot more friction at the surface, and at a certain level in the atmosphere, we basically don't have friction. So when we're dealing with upper level winds, and we're using the southern hemisphere as an example, notice for a second here that even though we're dealing with the southern hemisphere, mid-latitude regions of the southern hemisphere also flow from west to east. But then when we get to the surface, we see that the wind is actually crossing the isobars, but not directly into the low, but at roughly 45 degrees. Again, this would be geostrophic wind. And then this is wind at the surface. Notice this is the resulting wind, and it's crossing that isobar, oriented from high to low, not going into the low directly, but crossing it at that 45-degree angle. Okay, so earlier today I told you that we have these in the upper level parts of our atmosphere, we don't plot pressure, we plot height. So I want to talk a little bit more about that. Let's say, for example, we have uniform temperatures across this region within this box. Then as we go higher up into the atmosphere, we know that the pressure will decrease. Again, it's like 1013 on average at sea level, but if we go up to, let's say, 3,000 meters on average, we would see a 700 millibar reading. Eventually, as we go higher up into the troposphere, we would get into very, very small pressure because there aren't a lot of molecules on top of you to exert air pressure. When we start seeing temperature differences, for example, on the left we have warmer air, and on the right we have cooler air. Warmer air likes to expand, so the height of a 700 millibar value would be much higher because, let's say, it used to be at 3,000, but it warmed up, so all that air went upwards, so you have that pressure of 700 millibars farther up into the atmosphere. Conversely, cold air likes to contract, so it wouldn't take long for us to get to a certain level to have a pressure value of 700 millibars. So the height of a 700 millibar surface would be lower in colder air and higher in tropical or warm air. So these are the approximate, I like to just concentrate on the feet, for example. These are the approximate altitudes of various pressure levels. Now remember, this is just average. And the pressure values that we use most often are 500 millibars, because that's roughly halfway up the troposphere. And then we use anywhere between 300 and 200 for the top part, the upper level troposphere. So we have these in feet, and then we have kilometers over here, but when we're plotting these heights for a constant pressure level, we usually plot them in meters. So this is an example. So let's say for a second here, well, first of all, we will always have higher heights as we get closer to the equator, closer to 0 degrees. And then notice how the heights get lower and lower as you get closer to the poles. But it's not uniform. They often bend. So when these heights bend toward the poles like this, we call that a ridge. And when they bend toward the equator, we call that a trough. So ridges of high pressure, we often say ridges of high pressure. You see this word high right here. Or troughs of low pressure have they have such a strong influence on the weather at the surface. In fact, you cannot forecast or understand or even assess severe and hazardous weather unless we understand the upper and mid parts of our troposphere. So as another contrast, on the surface, we have a constant height. That constant height is basically 0 meters, and we plot pressure values in millibars. And we get our surface highs and surface lows, and then you notice how these winds are sort of crossing the isobars at an angle, at a 45-degree angle. But then, if you go up into the middle to upper part of our troposphere, we don't have friction, so then the winds will follow along the contour lines, which are in meters. And again, those meters get smaller and smaller as we go up unless we have troughs and ridges. So remember when I said that high pressure, the highest pressure reading that we ever had was due to extremely cold air. Now, that's not the only way we can get at high pressure. If we look at areas aloft, areas that are, let's say the mid to upper troposphere, if they are converging, if wind is converging, it has to go somewhere, so it tends to sink. So then when we have subsiding air, which is sinking air, we can create a high pressure at the surface. On the other hand, if we have diverging winds, winds that are getting fast, or basically the directions are, well, diverging, we need to fill in that extra space, so then we have air that rises to fill in that extra space. And that's how we get a lot of our low pressure systems. The low pressure systems, once again, are responsible for storms, for our winter rain, and even for severe and hazardous weather. So, convergence aloft causes air to sink, and diverging surface winds, which is what we call a dynamic high. A dynamic means that there's air moving. When we had a thermal high is when we have extremely cold weather that causes a much more localized high pressure. And then on the right we have divergence aloft, creating a low pressure, and that's a dynamic low because air is rising, there's movement. We could also get thermal lows, but those are smaller, and they're due to temperatures, usually very high temperatures. And there's your dynamic low. Another way to put this is basically the same thing, except I'm just showing you where we have the actual convergence of air, which is coming out of the ridge, and it sinks here. In fact, we're going to talk about Santa Ana winds here in a little bit, and these Santa Ana winds are often due to high pressure systems to the northeast of us. And then when we have divergence, which is typically to the right of a trough, we have low pressure systems. And again, low pressure systems can result in interesting weather, especially severe weather. Now a jet streak, so we haven't really talked too much about jet streams, but every once in a while aloft, basically, let me step back for a second. If we go higher up into the troposphere and we look at the 200 to 300 millibar levels, we see this river of air that flows from west to east, and we call that the jet stream. Now within the jet stream, we can get something called jet streaks, extremely fast moving air. And when we have that, we can often use these jet streaks to assess exactly where the severe and hazardous, not, I shouldn't say exactly, the general area where we're going to have severe and hazardous weather. It usually occurs near the low pressure system and also in and around the cold front. So if we had to choose a specific place that most severe weather occurs within this low pressure system, it would be near the cold front. We'll talk more about fronts in a future lecture. Alright, so to keep things pretty simple here, low pressure centers typically cause those clouds, precipitation, and even storms. High pressure systems fair weather most likely. Sometimes with high pressure systems, there's not a single cloud in the sky because air is sinking, and sinking air does not cause sinking air. They're just not. It's not conducive to create clouds. And if there are clouds, they're usually really high level clouds that don't really have a lot of height associated with them, or even shapes. They're usually cirrus clouds. Okay, so now we're going to get into chapter 17 a little bit here. Chapter 17 talks about downsloping mountain winds. There are various types of downsloping winds. Chinook is a type of downsloping winds that you see east of the Rocky Mountains. Sometimes they call these things snow eaters because, for example, Denver, Colorado may have snow, but when we have these warm, dry winds flowing off the east side of the Rocky Mountains, these warm, dry winds can very quickly melt snow. Around here, the most famous downsloping wind is the Santa Ana wind. So what are Santa Ana winds? First of all, they are typically warm, not always warm, typically warm, almost always dry, and they come from the east or northeastern direction, and they flow from higher elevation and from the desert, high desert really, and then go through mountain peaks and into canyons and passes. They can really spread fires and create disastrous wildfires. Now, a lot of people think the Santa Ana winds are warm because they come from the desert. That's not true. The peak of Santa Ana wind season is in December. So the deserts are actually quite cold. What happens is that these winds are coming from higher elevation, and when they sink down towards sea level, they get compressed. Just like when we were talking about the formation of clouds with air parcels. When air parcels rise, they expand and cool down. So conversely, when these, let's say, parcels of wind are coming down toward the surface, they get compressed and they warm up. If you compress air, it typically warms up. This is a typical setup. This is an extremely simple map, but one that I want to highlight because one of the clues, especially if we're going to forecast Santa Ana winds, is we need a strong high pressure to the northeast of us. So that high pressure could be somewhere in Nevada, Utah, maybe even southern Idaho. And that pressure, sometimes we call it the Great Basin pressure. So we have this high pressure, and what kind of rotation do we have around a high pressure in the northern hemisphere? We have clockwise. So air is moving clockwise, but then as it approaches lower pressure, sometimes we have a low pressure center offshore, or we just simply need lower pressure. Then it will not rotate indefinitely around the high, but it will cross these isobars at a like a 45-degree angle and cause our easterly winds. Notice that these values northeast of us are colder, but once it gets down towards sea level, they warm up due to adiabatic compression. Here's just another setup. You might see this on the local news. That helps us understand not just if we're going to have Santa Ana winds, but if we look into the details of the pressure gradient, we can look into how fast these Santa Ana winds are going to be. That can be very, very important because we need to know if high-profile vehicles should be extra cautious, if we really need to make sure that we don't start fires or have any kind of fire starting equipment, whether you're camping or you're smoking a cigarette. You just got to be very careful when we have these, because it's not just the speed, but it's also how dry. These winds can be extremely dry. Relative humidity values can be as low as 1%. In the fall of 2019, when we had a Santa Ana wind event, at Pierce College we had a relative humidity value of 2%. And the dew point value was somewhere around -10 degrees Fahrenheit. So that's extremely dry air. We could also look at soundings, or a QT diagram. If we notice we have very dry air in the Great Basin, and we have northeasterly winds, and even an inversion, which I'm not going to get into here, but typically an inversion also can help us understand that we have prime conditions for Santa Ana winds. And unfortunately, when we have Santa Ana winds, we often do have wildfires. Now, because these fires are, or I shouldn't say the fires, but the winds are coming from the northeast, we see much of that smoke going offshore. So areas that are typically nice and clear because of sea breezes, like Catalina Island, will often see poor air quality conditions because of these winds pushing that smoke toward the island. Just here's some other graphics that you might see when we're looking into Santa Ana winds. The season for Santa Ana winds typically starts in late September, early October. It peaks in December, and it sort of wanes very slowly from April to May. Essentially, we do not have Santa Ana winds during the summer. We don't have the large-scale setup of this high pressure to the northeast of us. Usually that high pressure is over here in the form of the Pacific high in the summertime. And these are just some images of Santa Ana wind results. You know, these winds can affect not just high-profile vehicles, like I said before, but trees, power lines, even gas stations, and unfortunately wildfires are some of the worst types of hazardous conditions that we can have around here in California. And this is just another graphic of that wildfire, the smoke that's moving offshore, creating terrible air quality conditions in the ocean. So I hope this makes you understand a little bit about how air pressure and wind are related, how wind and speed are affected by different forces, and how all of these concepts result in understanding Santa Ana winds, which is one of the most unique hazardous weather conditions we have here, and how these winds can affect wildfires, which is another unfortunate but important hazardous weather that we have here in Southern California. Thank you, and see you next time.